Okay, this week we will be discussing the electric potential energy and electric potential, and we will try to make especially the distinction between these two concepts to be clear. But before the potential and potential energy discussion, do you have any questions about the electric field, the Coulomb law, the Gauss law? Any questions, anything you want repeated? Now, the potential we will discuss now. So just keep your questions for our discussion on potential.
About the flux.
Yes.
If we define the net flux as zero in some area, the electric field exists, but the flux is zero. I don't understand why we need it to be zero. Why we define it to be zero?
We don't define it to be zero. It turns out to be zero. I mean, you see, if we repeat the statement of the Gauss law, what it says is that you take any arbitrary closed surface, the total flux inside is determined only by, the total flux on this surface is determined only by the charges inside. So if the enclosed charges is zero, that means the total flux passing through this surface, this closed surface, is zero. But this doesn't necessarily mean that the electric field itself is zero.
So what does it mean?
Well, this just means that the electric field is pointing towards the inside in certain regions and towards the outside in other regions. That is what this expression means. Now, one example where we had where the electric field is not zero, nevertheless, this integral is still zero. For example, just take the point charge. Put some point charge over here. Then we know that the electric field at this point is pointing in this direction, whereas the electric field here is pointing outward. So this point, if we define the inside to be this volume, the electric field here contributes negative to this integral, whereas the electric field here, it contributes positively to this integral. And they just sum up to zero. That is what this expression means. So the electric field is in certain regions pointing towards inside. In certain other regions, it might be pointing outside.
It has no other physical meaning.
Well, what kind of physical meaning are you looking for? Now, we will use this concept of flux quite often. Here is the electric flux. Later on, we will use the concept of the magnetic flux. And even later, we will be talking about the energy flux. In that case, this will have a more physical meaning. It's the amount of energy. It will be, if we are talking about the energy flux, it will be the amount of energy moving through this surface. But in this case, not really. The only thing it says is that in this region, there are no charges if E dot dA is equal to zero. Other questions?
There is formulas, and the inner ones have positive sigma, the outer ones have negative sigma. So what is the electric field at the inner unit?
So this is the question. We have two infinite planes with plus sigma, and two more infinite planes with charge densities minus sigma. So the electric field. Let's look at the electric field everywhere. So basically, we need to find the electric field in 1, 2, 3, 4, 5 different regions. 1, 2, 3, 4, and 5. In these 5 regions, let's just give them some names. Let's call this one plate 1, plate 2, plate 3, plate 4. 1, 2, 3, 4, so that we have the electric field created by the plates. We can just denote them by EI. So EI is the electric field created by the plate I. And the electric field at any point will be just the sum of the electric fields, E1 plus E2 plus E3 plus E4. No, there's no 5. We only have 4 plates. We have 5 regions, 4 plates. Now let's look at, we know that all of them, since they correspond to an infinite plate with the same charge density, the magnitude of EI is always sigma over 2 epsilon 0 for all of the I. So they all have the same magnitude. They might be pointing in different or the same directions. Now let's draw their directions. In region 1, what is the direction of E1? E1 is the electric field created by this plane, which is negatively charged. So it's always pointing to the plate 1. So let me open up some space. So this is the direction of E1 in region 1. And in region 2, 3, 4, and 5, it's always pointing upward, because it will be always pointing towards the plate, since the plate is negatively charged. This is E1. Now, what about the E2 in region 1, the direction of E2? You see, E2 is the electric field created by the positively charged plate. The electric field will be always pointing away from the positive charge. So it will be, in region 1, it will be upward. In region 2, upward. Region 3, downward. Region 4, downward. 5? Okay. So let's look at E3. This is E2, the direction of E2. E3, it is the electric field created by this plate. It's positively charged. It's always pointing away from it. So in region 1, region 2, and region 3, it's pointing upward. In region 4 and region 5, it's pointing downward. This is E3. Now let's look at E4. This is a negatively charged plate, so the electric field is always pointing towards the plate. So it is downward in region 1, downward in region 2, downward in region 3, downward in region 4, and upward in region 5. So these are the directions of the electric fields created by each one of those plates. Now, in an arbitrary region, let's start with E1. What is the electric field in region 1? We see all of these electric field contributions to the electric fields, they have the same magnitude. So one is pointing down, one is pointing up. These two cancel. These two also cancel. So the electric field in region 1 is just 0. Electric field in region 3. In region 3. I'm not looking at 2. I jump to 3. 0. Up and down they cancel. Up and down they cancel. So it's again 0. So that's the answer to your question. Now the electric field in region 5. 0. Let's see. E1 plus E2, it gives me 0. E3 plus E4, it gives me 0. So the electric field in region 1, 3, and 5, they are all 0. Now let's look at the electric field in region 2. Okay, it will be non-zero. Let's say this is our z-axis. Okay, this one and this one, they cancel each other. We have two electric fields with the same magnitude pointing in the same direction. So the sum would be just sigma over epsilon 0. It's in the positive z direction. And the electric field in region 4, E1 plus E2 will be 0. So I have two electric fields pointing downward. Both of them have the same magnitude, sigma over 2 epsilon 0. So the sum has the magnitude sigma over epsilon 0. And it is in the minus z direction. So if we draw the electric field lines, this is plus sigma, minus sigma, minus sigma. The electric field lines are pointing upward in this region. They are pointing downward in the other region. Okay, this is just explicit calculation. But we could have also done this thing. Let's first imagine we bring this one, this minus sigma charge. And then we bring this plus sigma charge plane. We all have already studied this two-planar charge distribution. We know the electric fields. The electric fields are pointing from the plus sigma to the minus sigma plane. They will be uniform. Outside, the electric field will be 0. Then I bring this third plane. But now there is no electric field left. So this plus sigma plane doesn't feel the charges over here. So it will be, I will bring it. There will be a plus the electric field created by this one. And then when I bring this one, well, this is just let's say independent two infinite planes. And we know the electric field. Again, uniform, pointing from the positively charged plane to the negatively charged plane. Well, this you might not be able to see at first sight, but this first method, it works all the time. Just consider charges separately. That is what we did. We already knew the electric field created by an infinite plane, so I can just consider the electric field as a superposition of all the charges. All the electric fields created by each one of those planes individually, just superpose them. Well, of course, if the plates are not infinite, these will be just approximate solutions away from the edges. If you go closer to the edges, they will not be uniform. Well, the other example, as your friend points out, how many spheres? How many spheres? Kaç küre? Okay, two spheres, one inside the other one. So do they have the same charge or same charge density?
Same charge density.
Okay, so what are the charge densities? Okay, what are the charge densities, or what are the charges? Or are they arbitrary, Q1 and Q2? Positive Q1, okay. Positive Q1 minus Q2? Uniformly distributed? So we have all these minus charges. Here we have all these positive charges. Let me just write down immediately the electric field. Let's divide it into various regions, 1, 2, and 3. Electric field in the first region. I have uniformly charged shells, and I'm inside those uniformly charged shells. It is 0. Now let's look at the electric field in region 2. I take some point over here, and the electric field will be all the time the superposition of the electric fields created by the charges separately. So the electric field in region 2 will be the electric field created by this shell plus the electric field created by this shell. I am out of this shell, so this shell just behaves like a point charge. So E2 will be 1 over 4 pi epsilon 0, Q1 over R squared, R hat. And I'm inside this negatively charged sphere. So the contribution of this sphere to the electric field here is just 0. So we are inside the shell, inside the uniformly charged shell there is no electric field. If you imagine this one, this is my R. Now the electric field, well, this R vector is the vector pointing from the origin to the position at which you are evaluating the electric field. So if you change the position, that R vector also changes. Now the electric field in region 3. I'm somewhere here or here. I'm out of both of these shells. So the electric field created by the inner shell will be just as if it's a point charge, 1 over 4 pi epsilon 0, Q1 over R squared in the R direction, plus I'm also out of the second shell. So it will also behave like a point charge. So it will be 1 over 4 pi epsilon 0 minus Q2 over R squared R hat. Well, you see, this R depends on at which point are you evaluating E. So if you are in this region, this should be the expression that you should use to evaluate the electric field. And let's say if you are looking at the electric field at this point, this is the R vector. If you are looking at the electric field at this point, this is the R vector. And similarly, if you are at somewhere in this region, out of both of the shells, then this should be the expression that you should use to evaluate the electric field. And again, this R vector depends on at which point you are evaluating the electric field. So let me write it explicitly. R at the point R at the point R. So if you look at this point, then this should be the expression that you use, and the R vector is this vector. Well, you see, you have to specify me what the question is. So do they have, if they might have the same charge, then Q1 is equal to Q2, this is 0. They might have the same surface charge density, that means Q1 and Q2, they are different. They might be conducting and have a thickness. Well, if they are conducting and the thickness, then inside these conducting regions, the electric field will be 0. And if they are non-conducting and have a thickness, and the surface charge, the charge is again, but the charge is on the surface only, then nothing will change. If they are non-conducting and the charge is distributed uniformly on the thickness of this shell, then of course you have to calculate what is the enclosed charge. But the method will be basically identical. Okay, you see, if you have, this is the inner sphere, let's say, and we have this shell. And everything is conducting. Well, if it is conducting, we know that the charge can only be on the surfaces. It cannot be inside, because the electric field here would be 0. The electric field here will be 0. And there cannot be no charge inside these conducting regions. So let's say this is the region 1, this is region 2. Those are the only places where you can have an electric field. If they are uniform, then if you are in region 1, the outer shell doesn't contribute. The inner shell just acts like a point charge. Nothing really changes. If you are in region 2, again, both of these, both the sphere and the shell, they behave like point charges. And again, we have exactly the same expression in region 1 and region 2. The change from the previous example would be, well, in region 0, again, there is nothing changes, 0 electric field here. Only in this shell, the electric field will also be 0. That's the only difference between this example and this example. Let's look at this other example, which will be different. Can you repeat? Can you clarify your question?
Yani surface'ı ne kadar genişletirsek içinde o kadar çok fazla yük olacak ve o yükler de içeriye aslında elektrik alana etki etmeyecekler, sık olacak.
So what you are saying is that should we take larger and larger spheres?
İşte nedenini anlamıyorum. Yani surface'ın içindekinin sıfır olmasını sağlayan şey veya o surface'ın içinde gösterdiğimiz şey ne olabilir?
So if I understand your question correctly, why is the electric field inside the spherical shell zero? It's basically cancellations. So you see, if you are, let's say, if I forget this one, I consider some point over here. The charges on this surface will create an electric field. In this region, will create an electric field here. The charges here will also create an electric field. The charges here will also create an electric field. What happens is when you sum them up, let's assume this is positively charged, so we have some electric charges on this region, and they will create an electric field in this direction. Whereas the charges over here, they are also positively charged, they will create an electric field in the opposite direction. When I sum them up, they just give zero. They just cancel. It's not that there is no electric field. The net electric field is zero. There is, of course, all the different charges on the surface. They do contribute to the electric field over here, but their contributions are such that the sum gives me zero. That's the reason why in a uniformly charged spherical shell, there is no electric field. If it is not uniformly charged, or even if it is uniformly charged, if it is not spherical, the electric field inside will not be zero. You mean this shell goes to infinity? Okay, fine. Well, if they are infinity, there's no way they are creating any electric field, any one of them. Oh, so you are saying that I have this surface, I'm close to this surface, and the other parts of this surface are all at infinity. They are infinitely far away, so they cannot create an electric field. Nevertheless, I am closer to this side, so there will be an electric field here. Is that your question? But remember, I agree, all the other charges are infinitely far away, but the charge there is also infinity. Fine, no problem. But you see, the thing is, the charge over here is finite, that you are close to. You are putting infinite amount of charge at infinity. So they still contribute, although the distance goes infinity. Let me just mention the other example. This one. Everything insulator. Charge uniformly distributed. Over the volume. And you can have the charge density is, let's say, rho 1 here and rho 2 over here. Then, of course, this becomes a more complicated example, but the basic principles are still the same. So if you are, let's say, if you want to find the electric field at this point, The only thing you have to do, since everything is spherically symmetric, just imagine this hypothetical sphere this point is out of all these shells making the inner charge and this part of the shell. So all of these charges, you have to just, using rho 1 and rho 2, you have to calculate the total charge inside this red surface. And all that charge will act as if it's a point charge at the center. And these charges on the outside of the sphere, they will not contribute to the electric field. And so you know the electric field. It just becomes technically more complicated, but nevertheless, the basic principle is the same in all the previous problems and in this one. So you just imagine this sphere whose center is the center of your system, and such that this sphere is, your point lies on the surface of the sphere. You have to calculate the total charge inside the sphere. And that charge just acts as if like a point charge, and you know the electric field of a point charge at the center. In all these examples, we had done exactly the same thing. We just imagined this, no, not the first one, starting from this one. Well, if you are in region 3, the only thing we did is we imagined this sphere, the total charge inside is Q1 minus Q2. So if you look at here, this is nothing but Q1 minus Q2 over R squared. That's the electric field of a point charge. In this one, again, we did almost the same thing with an additional information that in a conductor, the electric field is 0. Out of the conductor, we use the same principle. In this problem, you can imagine even 3 shells, 4 shells, no matter how many shells, the principle is still the same. Just imagine this sphere with its center at the center of your system, and your point is on the surface of the sphere, and calculate the total charge inside that sphere. What is the electric field of a point charge with that calculated charge at the point? That's the basic idea.
If we consider the surface of one of these spheres as an equipotential surface.
Equipotential, we didn't define it yet. We don't know what that is yet. Other questions? There was one over there.
In this example, there is no charge on the surface of the sensor.
No, everything is distributed over the volume.
Inside.
Inside. Okay, now let's review some potential. The first one. No, they don't. Because the electric fields are isolated within these plus and minus plates. Sure, ideally in an infinite plane. If you have an infinite plate, or if you don't want to have an infinite plate, you can just take 2 spherical shells like this one and choose set Q1 and Q2 equal. If Q1 and Q2 equal, you have an electric field only in this region. There's no electric field outside. You can create finite regions which have electric fields. And outside, there's no electric field, like this one. Other questions? Okay, let's review our understanding of work. Work and potential energy. This is basically a review of what we had covered in mechanics. Now, if you have any force, Now, in this course, we will be applying this to not an arbitrary force, but the electric force. But the definition of work is valid for any force. Then the work done by this force as you go from point A to point B, we define it as this integral. Now, what this integral basically means is that you start from point A, you take your object and move it to some other point B. This is your point B. Now, the object need not be moving only under the influence of this force F. F is some force acting on my object, and there might be other forces acting on my object. And under the influence of all these forces, the object is moving from A to B. For example, I can take this thing, this book, with your quizzes, and move it around from point A to point B. Of course, what determines this motion is the gravitational force and the force that my hand is exerting on this book, and also the friction force due to the air, atmosphere. But I can still talk about the work done by my hand or work done by gravity. Now, what these symbols mean is that just take this path, divide it into very small segments. Well, since I'm going from A to B, let me also put this arrow. I divide it into very small segments. In each one of these segments, let's take this one, I go from this point to the next one. The vector pointing between those 2 points is what I call the vector dl. And at that point, there is a force acting on my object, and the force can be, let's say, in this direction. And the work done in this segment by this force F is defined as F dot dl. I have these two vectors. I just take their scalar product. And this is the work done only in this segment. I just sum all of them. And that gives me the total work. This is how we define the work done by a force.
We don't know the exact direction of the force.
I mean, for a given if you want to calculate the work done by a force, you should be better know the force. I mean, if you don't know the force, there is nothing to calculate.
No, I mean the direction, not the magnitude.
I mean, knowing the force means you know the direction and the magnitude. So to calculate this, you have to know what the force is. You have to know the trajectory of your particle. And in general, this sum depends on how you go from A to B. If you go from A to B along this path, you will have one kind of work. If you go along some other path, you will have some other kind of work. One example is the friction force. Let's say we take this book on this frictionful surface, and let's just assume that A and B are the same point. Well, if it stays there, I went from A to B. There is no displacement. The L is always 0. So since the L is always 0, whatever the force is, the work done is 0. If that is my trajectory, it just stays there. That's the trajectory of this object. Or else I can just imagine I take this book, slide it in this direction. Well, this is the direction of the L. This is the direction of the friction force all the time during this motion. So the work done by the friction force is negative. And then I just move it backwards to the initial point. As it's moving backwards, this is the direction of the L. This is the direction of the force. And again, the work is negative. And when I come back to the initial point, the total work done will be the sum of negative numbers. All of these ones will be negative, so the total work will be negative. So this is an example of a force for which the work done as you go from 2 points, which can be the same point, depends on your path. Now, such forces we call non-conservative forces. And a conservative force is a force for which the work done is independent of path. One example is gravity. We had seen that gravity is a conservative force, or in fact, any constant force, it will be a conservative force, because let's take this book, I lift it upwards, the dl is in this direction, gravity is pointing downward, so the work done by gravity as I lift this book is negative. Then if I move the book back to the initial point, gravity is downward, dl is downward, so the work done is by gravity is 0. That is one path from this point to this point. Or I can just hold it at the same point. Again, these are two different trajectories with the same initial and final points, and both of them have the same work. And you can actually show that for a constant force, it is always true. Now, to say this, okay, let's just look at the expression of the work from A to B. Well, if the force is constant, I can just take it out. This will be the force, scalar product from A to B of dl. But you see, this is, now let's see what this means. We have a path, we divide it into very small segments, and dl is our displacement, and each one of those segments, if I sum my displacements, I obtain the total displacement. But my total displacement is nothing but the change in my position. So you see, a constant force, the work done by a constant force depends only on the initial and the final points. It doesn't depend on how I go from one point to the other point. Now, this the constant force is one example of a conservative force, but we also know other examples that are conservative, like the gravitational force, which was the Newton's constant m1, m2 over r squared in the r direction. This is a conservative force. We had proven it in mechanics course that this is conservative. But if that is conservative, the electric force, which is 1 over 4 pi epsilon 0, q1, q2 over r squared in the r direction. This is, mathematically speaking, these are identical forces. They are the same force. They have the same mathematical expression. So these are all also, both of them are conservative forces. Now, if you look at this one, we said that for a conservative force, the work done as you go from A to B depends only on the initial and the final points. Now, if you look at this example of this conservative force, you see that, in fact, the work done is nothing but the difference of two functions, and each one depends only on, one of them depends on the final point, and the other one depends only on the initial point. And that function is what we call the potential energy. So for a conservative force, F dot dl from the point A to the point B, this is equal to U of B, no, U of A minus U of B. This integral, just like this one, for any conservative force, we can write it as this difference. And if you just look at this one, for a constant force F, UA is nothing but minus F dot the position of the point A plus, let's say, U0. Now this U0, well, you see, when we calculate the work done, we calculate the difference of the potential energy of the system between these two configurations as it goes from point A to B. So if you just add a constant term to everything, it doesn't change this distance. So we cannot determine this constant over here. It's always there, but we can just fix it by some convention. We can say that the potential energy of the system, let's just assume it is 0 when the system is in such a state. For example, in the case of the gravitational force, we can say that, okay, when the book is over here, its potential energy, let's just take it to be 0. It's just convention. It's just like choosing an origin in your coordinate axis. You can choose any point as your coordinate axis, or as the origin of your coordinate axis. You can choose any point to be the 0 potential energy point. Now, this was just a fast review of what we had done last semester. Now, any questions on potential energy and the work done? Now, in the next hour, we will be applying these things to the electric force. We will be talking about the electric potential energy of a given system, from which we will be talking about the electric potential also. So, some questions. U0. Well, you see, this is how we define the potential energy as the differences. The potential energy between the point A and point B is the difference between these two functions. We only know these differences. Now, I can assume that for the constant force, let's say, we already know what that difference is. We had calculated it. You see, for the constant force, we had calculated the work done as you go from some point A to the point B is this function over here. So the obvious choice seems to be UA is equal to this one, if you just look at the previous expression. But if I add this number, which is an arbitrary number, I'm not changing this difference. So there is nothing that will help me to determine that number. Or if you look at the definition of the potential energy differences are defined. But if you add some constant to this one and to all the potential energies, if you add the same constant, you are not changing the differences. So that is why we cannot determine this number. But we can fix it by some means. You can say that the potential at this point, let me assume it to be 0. That would allow you to determine what this constant is. No. It is defined like this. We will come to that point in a moment, in the next hour. There is a minus sign difference over there. Y is here. Well, let's look at this one. For a constant force, this one is equal to minus F dot RA plus F dot RB. This is for the constant force. So UA is this one, UB is minus this one. In fact, for an arbitrary point, let me just remove this A. U at the point R is in fact this one. There was one question on the back. Okay, not anymore.
Potansiyel enerji orijin istediğimiz yerden olarak aslında arttırabiliriz. Fakat o zamana bağlı bir fonksiyon olarak ilerlediği için hızını bulurken yine kullandığımız biz elektrik force'la zamana bağlı olan fonksiyon hangisi?
Now, we don't have time-dependent forces. We won't have time-dependent forces yet. So there's no time dependence over here. Now, also, for example, if you are talking about the connection with the work and kinetic energy theorem, it states that the change in the kinetic energy is equal to the change in the potential energy. Again, in changes. If you add a constant to everything, the change does not change. The difference does not change. So whatever you choose this U0, your conclusions will always be valid because all the results that we obtained about the potential energy are, in fact, the results about using the potential energy differences. And that constant doesn't change the difference. Okay, see you after the break. You can pick up your quizzes during the break.